esReven has always strived to provide the best-in-class solution to do full system timeless analysis on the x64 platform. But wouldn't it be great if the same solution worked on ARM platforms as well? Well, we've been working on this idea for a while, and now we have a technical demonstration that we can show you. So in this video, we will look at this very early build of esReven Arm. So this is it, exciting, the very first build of esReven Arm. As you can see, it looks very similar to esReven x64 for those familiar with it. And obviously we are focusing on the Android platform at the moment. Before we start, it's very important to note this is not yet a product. There's a lot of R&D to do on our side. This is just a very early build. And the goal here is to define and refine the usage and use cases that this could target, okay? So with that being said, what do we have in this trace? Let me zoom in on the frame buffer. We've recorded the launch of an application. The application is something that we've built for this demo in order to show just a couple of things that we think might be interesting to look at. And we can see what happened in the trace. So first we had launch the launcher, then we moved the mouse over to the application, we clicked, we started the application, and at the end the application is started and we see a message on the screen. So for those not familiar with esReven, what we have is not just the trace of a single application, we had the entire VM running in here. We can see that by looking at the trace filter on processes, where we see all the processes that have some code running in our trace, and there's quite a few. And that's going to help us in a moment. But for now, what can we look at in a trace like this? So because the esReven is focused on native code, but this is a Java application that we're recording, a prime target for things to look at is going to be calls to native library functions. The application bundles its own library and then making calls to that. We have such an example here. Our application makes a call to a function called native sort. And this function exists within a library that it bundles. And at that point, this is regular esReven. We have the native code running. We can see calls to the general environment made by this function. So in this case, JNR environment is fetching data from the Java side of things and using that itself. It's a sort function, so it's going to get the pointer to an array, make modifications to it, and then set that array again and release everything. And so yeah, this is very easy to look at. And this use case here is very interesting when we have maybe a protected application through a RASP, for instance, where it's going to try and implement those protection in native code in libraries that will be decrypted during the life of the application. And so those function and those code locations might be really hard to find in static analysis, but here the application is going to do its thing. So you will see those function calls made and you will be able to see what they actually do on the system, and so understand how the protection works very, very easily. So that was the first obvious thing that esReven can look at. So the second usual use case is doing root cause analysis with esReven, especially when tracing the root cause goes through multiple processes. This is usually very hard when using a single debugger, but of course with a full system trace, it gets easier. So let's look at such an example. We had seen the list of processes that were executed during the trace, but we can also look at the processes that were started during the trace using the Python API. So we see our application starts a shell with this command, echo root into dev null, and then calls ID, and so shell starts ID at some point, and you can probably guess where this is going. If we look at the execution of the ID, this is the ID main function, get UID, then printf. Yes, of course, I am root. So I have an observable event here and I want to trace it backwards. And notice that I'm not in the application process anymore. This is a completely different process, and I was able to fairly easily find that. So we don't have the taint on esReven Arm yet, so we'll have to do things manually here. So get UID, we dive in the kernel code. There we are using the call tree. We can trace things. Okay, this is the get UID, and this is where the ID is actually stored. So bear with me for a second. We're going to do some manual data analysis. So previous write comes from memcopy because ID was forked from the shell process itself. So we're going to trace that a couple of times. Second time, same thing, tracing that backwards. Oh, every time I'm looking at the source and taking the previous write. There we go. And this is where we wrote something. So this was my ID 27E9 and we overwrote 0 on top of it. And this is just made by a function that we modified in the kernel image in this case. But the use case here is you would be looking at a privilege escalation in the kernel, for instance, or a bug being executed. So the usual esReven use case where you have a proof of concept or an exploit and you want to run that, even if it comes from an application, it's very easy to record and trace that through all the processes. So that's it for this early build of esReven Arm. If you are interested in discussing how it can fit your use cases, from analyzing RASP, the kernel, drivers, bootloaders, or others, we'd be very interested in having your feedback. In the meantime, of course, thank you for watching that video.